sound coming from the. But is it okay back there to listen to my voice?
You can use a microphone.
Okay. So I can use this microphone. Okay, this is good, right? Okay. Thank you again for coming to this talk. Today's speaker is Professor Masashi Sugiyama from RIKEN and the University of Tokyo. I know Masashi very well, and I have many good words I can use to introduce him. He's the director of the RIKEN AIP, the Advanced Intelligence Project, right? And that is basically a huge institute having more than 40 PIs.
35 PIs.
Yeah, 40 PIs. And every single of them are very good, very renowned researchers. And basically he's directing all those people. I can say, he's the first Asian person who did the program chair and the general chair of the new list, and now he's in the board of the new list. And basically, due to him, many of the Asian people are now on the core new list community. In terms of the research, he has interest in the topics like the distribution shift and density ratio estimation and weekly supervised learning, weekly supervised learning. Okay. Well, those topics are about the situations that many people just overlook, but definitely necessary in the real applications. Maybe if you have some difficulty on your project or your work, probably that's this situation can be the reason that you cannot solve your problem. So there are many information that you can use in this talk. So I hope you enjoy this talk, and please join me to welcome Masashi Sugiyama.
Thank you very much. So actually in Tokyo, the temperature dropped from 35 degrees to 20 degrees the day before yesterday. And because of that, I had a problem with my throat. Sorry for my bad voice. But I tried to give a talk today with a microphone. So thank you very much for the kind introduction. And it's great to come to Hanyang University for the first time. So it's a great campus and beautiful campus. I really think it's a nice university. So my talk is about machine learning from imperfect information. But before starting, let me briefly introduce myself a little bit more. So as Professor No introduced, I'm currently director of RIKEN AIP. So I have a few more slides about RIKEN, so I will talk about a bit more in detail. Then I'm also a professor at the University of Tokyo, so in computer science. So we have many PhD students and master students. And also I'm advising some local startups, so they are also doing quite great jobs. Then my personal background is machine learning theory and algorithm. I'm very much interested in basic research. So usually I try to select one topic and work on that topic for 5 to 10 years and publish a book. So far we had 6 books on machine learning from non-stationary environments to machine learning from weak supervision. So all are quite technical books, but these are actually quite important goals for us to make a book out of our series of research. Then potentially, I'm also interested in applications a lot, but unfortunately, I'm not capable of really doing application jobs by myself. So I try to find partners outside, and I try to join some project on these application domains. Then, as Professor No introduced, so I was a program co-chair for NeurIPS and AI Starts, and at NeurIPS, he was a program manager, and we worked together 9 years ago, quite hardly. Then also I gave a keynote talk at iClear last year. So this conference was held in Africa, Rwanda for the first time. And that was really a nice experience for me to be in Africa. Then, so about RIKEN. So our institute in Japanese is written in six characters. So they are pronounced as Rikagaku Kenkyusho in Japanese. And the meaning is Physics and Chemistry Research Institute. But 6 letters in Japanese is too long. So we usually pick the first character and fourth character and attach them. So this is pronounced as RIKEN. And many years ago, RIKEN in English was like Research Institute for Physics and Chemistry or something like that. But at some point, RIKEN headquarters decided to use this Japanese acronym, RIKEN, as our official English name. So that means RIKEN is no longer an acronym in English. It's our official name. And RIKEN actually has a little bit longer history, started in 1917 as a private foundation actually. Then so it became a big organization. It was called RIKEN Konchan. So in 1939, RIKEN had 63 companies and 121 plants. It was really a big entity. And it was quite successful before the World War II. But because it was a successful organization, it was regarded as a bit dangerous entity. And after the World War II, RIKEN was broken up. But in 1948, RIKEN restarted as Scientific Research Institute, and then it became public corporation. And now RIKEN is called National Research and Development Institute. So we have more than 100 years history. The entire RIKEN is actually quite a big institute. So we have close to 3,000 researchers and 500 admin staffs. And roughly we have 15 research centers and projects. Yeah. Or is this the problem of the connector? Or?
Yeah, I didn't change anything.
Oh, maybe here.
Yeah.
Oh, yeah. Okay, so we have about 15 projects and centers like this, and roughly so 6 are physics-related research centers, and 6 are life science-related research centers, and 3 are informatics-related centers. So one is about robotics, the other is about computational sciences and supercomputers. Then our center, so Center for Advanced Intelligence Project. So then what is RIKEN AIP? So RIKEN founded the Center for Advanced Intelligence Project in 2016 under the Ministry of Education, Culture, Sports, Science and Technology. And we have about 130 employed researchers. And we have 40% international researchers and 25% female researchers. So it's quite diverse. And we have many visiting researchers, including Professor No, and 130 domestic students, and many international interns. Some are also from Korea. And then we have many collaborators and industry partners. And we are located in the center of Tokyo, actually 10 minutes walk from the central Tokyo station, and located in this kind of building. And also some teams are distributed across the entire country like this. Then in this RIKEN AIP, we have 3 research groups. The first group is called Generic Technology Research Group. So in this group, people are working on fundamental topics on machine learning and inference algorithms, including robust estimation, Bayesian inference, high-dimensional statistics, or more theoretical analysis like statistical theory and optimization theory, including convergence analysis and non-convex optimization, things like that. Then the second group is working on Goal-Oriented Technology Research Group. It is called Goal-Oriented Technology Research Group. And here there are 2 pillars. The first pillar is AI for science. So we try to use AI technology to boost scientific research, like cancer research, material science research, and genomics research. And another pillar is AI for societal problems, because we are a national institute. We try to contribute to society. Like we are working on natural disasters, elderly healthcare, education, and things like that. Then finally, the third group is AI in Society Research Group. So here we have more like humanity researchers. Like they are working on personal data management, AI security, economy management, ethics and governance, things like that. So all 3 groups are working together to achieve a certain goal. Okay, then that was the brief introduction of RIKEN AIP. So then let's come to the main part of my talk. It's about reliable machine learning. So nowadays, we can see like machine learning systems deployed in many places, but its reliability is really the key issue. And unfortunately, the reliability of machine learning systems can be degraded by various factors. For example, our training data may not contain sufficient information, imperfect information. So I call it weak supervision. But still, we want to train our system in a reliable way, only from weakly supervised data. So this is the first challenge. The second issue is label noise. So now we have big data, but usually big data is full of noise, partially because of human error or sensor error. So learning with label noise is really an essential issue. Then finally, data bias. So the world is changing over time. So our machine learning system should also overcome changing environments. Or due to some privacy reasons, we are not allowed to collect training data as we wish. Then, so we have potential bias between training and test data. So this bias should be somehow incorporated in the machine learning system. So improving the reliability of machine learning system is really an urgent challenge, and this is our main goal nowadays. So today I quickly give a kind of high-level overview of 3 topics. Then finally, I want to talk more about future directions. Then the first topic is weakly supervised learning. So all of us know that supervised machine learning is really useful. In particular, if you have big label data, machine learning systems are really useful in speech recognition, image understanding, language processing, etc. But in many other applications, like in RIKEN, we are working on some medical projects, natural disasters, robot control, brain signal analysis. So in those projects, collecting big label data is quite challenging, unfortunately. Then for solving these problems, so I want to say we want to train a machine learning system from a small number of data. But learning from small data is not statistically really possible. So instead, we decided to use so-called weakly supervised data. So I don't say we only have small samples. We assume that we have a large number of weakly supervised data. But from these weakly supervised data, we hope to guarantee that our system is reliable. So that's a challenge of weakly supervised learning. So let's take an example here. So a typical example of weakly supervised learning is called positive unlabeled classification, PU classification. So it's a standard binary classification problem. So we have positive data, negative data, and we want to separate them. But for training, we only observe positive samples and unlabeled samples. So unlabeled samples are basically a mixture of positives and negatives, and we don't know which one is positive and which one is negative. And we don't observe any single negative data. So potentially we have red points here, but those red points are completely missing here. And only from positive and unlabeled data, we want to train a standard classifier that separates positives and negatives. So that's the goal of PU classification. And here is a textbook example of PU classification. So that is advertisement click prediction. So suppose certain advertisement appears on the screen and a user clicks it. Then so this advertisement is regarded as a positive sample because the user liked it. Suppose another advertisement appeared on the screen and the user didn't click it. Naively, we may want to regard this unclicked advertisement as negative sample, but unfortunately, so it is not really true. So maybe user disliked it, that's why he or she didn't click it, or maybe he or she was interested in that advertisement, but they didn't have time to click it, or they click another advertisement. So this means an unclicked advertisement is basically an unlabeled data. There can be either positive or negative data. So then in this scenario, so we naturally only have blue points and black points, and no red points. But still, we want to separate blue and red. So that's a typical PU classification example. Then, so I don't really go into the detail, but we somehow try to estimate the classification risk in an unbiased way, only from positive and unlabeled data. So today, I don't really go into the technical detail, but we can quite, in a straightforward way, we can obtain an unbiased risk estimator that can be computed only from positive and unlabeled data. So then, so we have actually a nice application of this PU classification. So it's signal enhancement. So the goal is actually quite simple. So we are given noisy signal, noisy speech, and we want to just denoise it and obtain a clean speech. So that's a task here. And typically, so to train such a system, we need a so-called parallel training data. So parallel training data means for the same signal, we want to have a noisy version and clean version. Then by comparing them, so we can train the system. But in practice, obtaining such a parallel training data is not really possible. Then people usually generate a synthetic noise and add this synthetic noise to true signal, clean signal. But unfortunately, such synthetic data does not generalize quite well in practice. Then, so in our formulation, we just use PU classification. So in our case, the positive class is noise, and the negative class is speech. And first, we put a microphone in some noisy environment and just collect pure noise. So these are positive samples, automatically labeled. Then, so we ask a subject to speak in this noisy environment. Then we have a mixed signal of speech and noise. So these are unlabeled data. Then, so we have positive samples and unlabeled samples, and we can just apply PU classification. Then, without observing any clean signals, we can separate noise and speech. And in the end, we can obtain clean signals. And signal to noise ratio is actually quite good compared with previous methods. Then that was like a first example of weakly supervised learning, so PU classification. But we have a lot more interesting examples of PU classification. And I just want to cover one more thing. So unlabeled classification, or UU classification. So this is actually quite interesting. So we don't observe any labels, but instead we have two sets of unlabeled data. So the first set here and second set here. And we assume that so class priors or class balance is different in two data sets. For example, in the first data set, maybe 70% are positive and 30% are negative. Then in the second data set, 20% are positives and 80% are negative, or something like that. Then only from the two sets of unlabeled data and class priors, we can train the classifier. So that's a bit surprising result, because we don't observe any single label, but still we can train the classifier in a guaranteed way. So for example, there are two hospitals and they accumulate a lot of medical images. But medical doctors are so busy that all the images are unannotated. This is often the case in reality. But suppose we have some additional knowledge that in hospital A, only 30% of patients are cancer. Then in hospital B, only 20% are cancer. Then only from two sets of unlabeled medical images and class priors, in principle, we can predict whether cancer exists or not in medical images without having any single label. So that's the potential application of UU classification. That's actually very interesting. Then we have a lot more extensions to multi-class problems, because labeling patterns in multi-class problems is even more painful. For example, in image annotation problem, image classification problem, nowadays we have 10,000 classes. Then we have a list of like 10,000 labels, and finding the right one takes a lot of time. Even if we use crowdsourcing or some other platforms, labeling data is quite costly and time-consuming. So to overcome this problem, we consider like some specific multi-class weak labels. For example, it's called complementary label. A standard class label specifies a class that a pattern belongs to. Like this sample belongs to class 1, or this image contains a dog, or something like that. But in this complementary label, we consider a complementary version. So it specifies a class that a pattern does not belong to. Like this sample does not belong to class 2, or this image does not contain a cat, or something like that. So only from such not label, we can actually train a classifier with guarantee. So that's complementary classification. Then we have a lot more variations like partial labels. So this corresponds to an OR label. So class 1 or 2, a dog or a cat or something like that. Or like single class confidence. So suppose we only observe one class data, but if one class data is equipped with full confidence, like class 1 with 60%, class 2 with 30%, class 3 with 10% or something like that, then only from one class data, we can train a multi-class classifier with guarantee again. So interestingly, all these different problems can be solved essentially in the same way mathematically. So it's quite a generic formulation. So altogether, so we propose an empirical risk minimization framework for weakly supervised learning. And this is a quite generic formulation. So we can actually use any loss function, any classifier, and any optimizer. And we may also consider any regularizers to be combined. So we summarized all the results and published a book 2 years ago. So it's machine learning from weak supervision. And more recently, so we are extending the results and try to have more unified frameworks and new problem settings and new algorithms. And also we try to explore more applications like in imitation learning and large language models and things like that. So weakly supervised learning is a quite basic concept, but it has actually quite a broad range of applications. So that's why we are so excited to have a book on this topic. Okay, that was about the topic on weakly supervised learning. Then the second topic is noisy label learning. So this is more simple. So we consider a quite standard supervised learning with noisy output. Okay, in the case of one-dimensional regression, we have input on the horizontal axis and output on the vertical axis. And instead of x, y, we have now x and y bar. Y bar is a noisy output like this. But in practice, we don't really care. We just try to fit our predictor to noisy output and minimize some loss function. In the classification case, so we have similar label noise, but this time it's label flipping noise like this. And again, usually we just fit our classifier to noisy labels. So hasn't such a classic problem been already solved in machine learning? For regression, actually, yes. As long as noise is independent additive, then so noise is fine. We don't have to care noise too much. As long as you have a large number of training data, noisy data, so we can guarantee statistical consistency. So we obtain a good solution. But in the case of classification, still actually we need a specific noise reduction mechanism to avoid overfitting. Even if we have infinitely many noisy labels, still our solution is not good enough. We need to have some special solution. And one typical approach we are exploring is correction with noise transition. So we consider so-called the noise transition matrix T. So this basically represents the probability of flipping label from one class to another. Like in the case of 3-class problem, we have a 3x3 matrix like this. And there's already a nice theory that, so if we know the noise transition matrix T, then so we can actually adjust the classifier to achieve good solution. So 2 approaches are proposed already. So this is a quite nice generic theory. But they need explicitly the knowledge of T. But T is usually not available. So we need to estimate it from only noisy data. So that's actually a quite technical challenge here. And again, I don't really go into the detail here, but we spent several years to estimate T only from noisy data. And finally, we end up in having a good solution to estimate T under weaker conditions. I prepared one technical slide, but again, I don't really go into the detail. But it's a simple sum of training loss and some regularizer. So we just minimize it. Then we can obtain a consistent solution and a reasonable solution, reasonable assumptions. Okay, that was one nice solution to cope with label noise. But unfortunately, the real-world noise is much more challenging. What we have considered so far was so-called input-independent noise. So noise property didn't depend on input X. So this means that noise property is essentially the same over the entire domain like this. But in the real world, maybe we have more label noise near the decision boundaries like this, because these samples are quite easy. So samples far away from the decision boundaries, they are easy to label. So somewhere near the boundaries are more difficult to label. That's why we have more noise here. But to really handle this situation, we need to consider the noise transition matrix function. So now t is a function of x. So this is far more complex and challenging to estimate. So in the end, we explored several heuristic solutions like this, and we had reasonable solutions so far, but they don't really have theoretical guarantee. So that's why we are further exploring new approaches, and I will come back to this point at the end of this talk again, because nowadays we are trying to approach this problem from a completely different viewpoint. Okay, then the third topic is about transfer learning. So training and test data often follow different distributions due to changing environments over time, or some sample selection bias issue due to privacy concerns. So training and test data may have different distributions like this. The goal of transfer learning is to train a test domain predictor based on training data potentially from different domains like this. And apparently this is not a new topic, and actually I co-organized a workshop in NIPS 2006. And at this moment, there was no name for this problem. So our workshop title was NIPS Workshop on Learning When Test and Training Inputs Have Different Distributions. So it really explains the problem clearly, but we had a nice workshop already almost 20 years ago. Then after that, so we had a book based on this workshop, and then we gave a name, dataset shift, for this problem. But more recently, so we have new names for this problem, like distribution shift and fine-tuning. In the last 3 years at NeurIPS, there were distribution shift workshops. And also this year, I co-organized a workshop at NeurIPS in December this year. So it's fine-tuning in modern machine learning. We also consider like foundation models and large language models in this context. So fine-tuning is also part of distribution shift research nowadays. Then here is some basics. So we consider simple setting called covariate shift. So only input distribution changes. So x is input, y is output. Only p of x changes. In the case of one-dimensional regression, so this covariate shift can be illustrated in a very nice way. So we have input x on the horizontal axis and output y on the vertical axis. And red function is the target function. So this is unchanged. And only input distribution changes. In the training phase, we have blue training points from the left-hand side of the domain. But in the test phase, we have black points from the right-hand side of the domain. And from blue points, we want to predict black crosses. So this is a typical covariate shift situation. And if we just perform linear least squares and fitting blue points, then we end up in finding this green line, and it fits blue points quite well, but it doesn't predict black crosses well. And we can show that this is not statistically consistent. But now, so we weight the loss function according to the importance. So importance is the density ratio between training and testing, so PTE over PTR. Then, interestingly, only from blue points and this importance value, we can obtain this green line. This predicts black crosses quite well. And we can show that this importance weighted training is statistically consistent. But in practice, this importance value is not known, so we should estimate it from data. So this was a technical challenge, and it's called direct importance estimation. And we want to estimate the ratio from training and test input data like this. And there are already two nice methods like kernel mean matching and least squares importance fitting. I don't really go into the technical detail here, but with this method, we can directly estimate the density ratio without really estimating each density separately. So they give a consistent solution. Then based on this kind of importance weight estimation method, so we can solve the covariate problem in 2 steps in this way. In the first step, we estimate the importance weight, for example, by least squares importance fitting, and obtain the importance ratio R hat. Then in the second phase, we plug this R hat into the weight here and obtain the final predictor F hat. So this was the kind of state of the art 10 years ago, and we had a lot of industry applications. And it was quite successful. But the potential problem is that the estimation error occurred in step 1. So R hat, we believe R hat is a good estimator of the density ratio, but still it contains some estimation error. Then in the second phase, second step, this small estimation error can be magnified because these two steps are performed independently. So somehow we want to integrate these two steps. By that, we hope that the performance can be further improved and stabilized. And here's a method called joint weight predictor optimization. It was just proposed a couple of years ago. And this is a so-called unlabeled unsupervised domain adaptation. So we are given labeled training data and unlabeled test data. And I don't really go into the detail, but we first drive an upper bound of the test risk. So it's J. And J is actually a function of the importance ratio and final predictor. And we minimize them jointly with respect to R and F. Then we obtain a guaranteed solution. And interestingly, this J function consists of two terms. And these two terms are exactly the criteria appeared in two steps. So this means that the classical approach corresponds to minimizing the upper bound in two steps. And clearly, this is not the optimal way. But now we are justified to minimize these two terms at the same time. Then more recently, we are extending this distribution research to so-called sequential shift. So far, we only considered training and test distribution. But now, test distribution can change over time like this. And we want to use some online learning scheme to update our solution to cope with this changing distributions. And so far, we had two works. The first work is about sequential label shift, where P of Y changes over time, so class proportion changes. And in the second work, we considered sequential covariate shift, so input density P of T changes over time. And for these two settings, we had a simple online learning scheme that adapt our classifier to new test distribution. And we have a very strong theoretical guarantee that this quantity is called a dynamic regret. And we can show that our online approach can minimize the dynamic regret without knowing the distribution shift amount. So this is quite interesting theoretical results. Then, I gave a quick overview of 3 topics so far. Then the final part is actually quite interesting, towards more reliable machine learning. So many distribution shift works focused on a particular shift type so far. For example, covariate shift. Only input distribution changes and the conditional does not change. But actually, identification of the shift type is the most challenging part. In particular, in our case, we assume that we only have unlabeled data from the test domain. Then basically, identification of the shift type is not really possible because we have no information about the test label. Then another issue was label noise. So actually, label noise is also a specific type of distribution shift. The P of Y given X changes between training and testing. In the training phase, we have noisy class label Y bar. And in the test phase, we assume we have clean labels and we want to estimate it, predict it. So PTR Y given X is different from PT of Y given X. And these two are connected with this noise transition. Then, as I have reviewed already, we had a nice theory and algorithm for input independent noise. So this noise transition does not depend on input X. But in reality, we need to handle input-dependent noise, and this is quite challenging. So this was still an open problem. Then our next direction is to consider a joint distribution shift. Now we consider P of X and Y, joint distribution changes between training and testing. This is actually a quite general formulation, and it basically contains everything. So P of XY basically describes the problem. This can be changed arbitrarily. So it's a quite generic formulation. Then in 2020, so we had the first solution to this joint distribution shift problem. But we need a strong assumption that we have a small number of labeled test data. So previously, we assumed we only had unlabeled test data. But in this paper, we require labeled test data like this. Then, so we try to estimate the importance weight dynamically in a mini-batch wise manner. So we use neural network and we use backpropagation, stochastic gradient descent. Then for each stochastic gradient step, we try to estimate the importance weight based on, for example, by kernel matching. So again, I don't really go into the detail here, but we use some existing method to estimate the importance weight dynamically. Then, so to our knowledge, this is the first method to systematically handle joint distribution shift. Then more recently, so we try to overcome the limitation of importance weighting itself. So in importance weighting methodology, we use this importance quantity, its ratio. So, but this ratio has to be finite. This means that so PTR cannot be 0. So this implies that the training domain must cover the test domain like this. So test distribution should be included in the test distribution. So this is a kind of implicit assumption in the importance weighting technology. But in reality, we want to consider this kind of situation. So test distribution is sticked out from the training distribution like this. It's a real extrapolation. But naively, this problem cannot be handled because the importance ratio tends to infinity in these regions. So how do we do that? So we had a nice out-of-domain extension to try to identify this point, so based on some outlier detection method. So we try to split our test data into the training part and test part by outlier detection method. Then for test data in the training side, we use the standard importance weighting technology like this. Then for the test data in out of training domain, they are pure test data. So we just compute the loss value for test data, and we just add them up. Then we can show that this is consistent. So we can systematically handle out-of-domain problems in this way. Okay, then so ongoing challenges. So far for joint shift adaptation, we assume that we have labeled test data, but this is way too strong in practice. But if we have only unlabeled data from the test domain, we can't really solve the joint shift problem. Then a good compromise could be to use weakly supervised learning. So instead of requiring fully labeled test data, we may require only weakly supervised test data, but hope that still we can guarantee that so we can really overcome the joint distribution shift. So this is still an ongoing work, but we hope our theory of weakly supervised learning is really useful in this context. Then finally, we want to extend this work to the sequential joint shift. So now P of xy really changing over time arbitrarily. So it's more like a generic formulation of continual learning or lifelong learning that has been studied a lot recently. Then in the end, we want to really have a machine learning techniques with least assumptions. So once we can reduce the necessary assumptions behind, then that method must be quite useful in reality. So that's our ultimate challenge for machine learning. Then this is the final slide. So nowadays we have large language models and foundation models in more general context. And so far, like let's say ChatGPT, so there's a central ChatGPT system and everybody uses the common system. But in real life, we may want to personalize AI systems. Already this is happening in some companies. Like each user want to download the foundation model and try to customize it. Maybe depending on the purposes or modalities, tasks, we may want to personalize them. Then, so we have many users and many AI systems at the same time. And so the world is changing over time. So we have many, like a big system like this. So something is changing over time, and we have many users and many humans, and they are interacting with each other. Then actually we have a lot of technical challenges in this context. So learning over time is one important issue, and we have many fundamental topics like this. and also learning across multiple AI systems and users. This is another important challenge. And then, so the entire system is quite big. Then computational efficiency and energy efficiency is another big challenges. And these are somewhat important topics for future machine learning systems because it's called online distributed machine learning. So I think foundation models are really used nowadays, but they will be really personalized, and we have many different variations. But hopefully, we have a kind of society-wide optimization of the entire systems. So they are not really independent, but they are cooperating each other, or maybe they are competing each other in some cases. But by looking at the entire system over time, we want to somehow control the update of the system, and hopefully we can guide the entire society system to the right direction. But to achieve that, we still need a lot of fundamental research on these topics. And this is something we want to pursue in our weekend center. Okay, so this is the last slide. Thank you very much.
Thank you. If you have any questions, I'm going to turn on the microphone for the audience. Maybe, yes, that's on. You can raise your hand if you have any questions and just talk. Right? Any questions?
Oh, yeah.
So you talked about this sequential learning. Is there any issue of capacitor for that?
So
In previous knowledge,
So
there are new shifts in the data,
new shifts.
in the sequential shifts.
Mm-hmm.
When you try to learn the new data, the shift, is there an issue of forget in the similar to the continual learning?
Right. In our current formulation, we only observe an unlabeled data set at each test domain, at each test point. But only from unlabeled data, we can really give an unbiased risk estimator, and we update our system based on online gradient descent. So this is how we maintain the statistical consistency in this way.
Okay, but you need the access to the previous data.
So okay, at this moment, we need entire training data. So that's why it's not really continual learning yet. So we need a kind of infinite amount of training buffer. So our future challenge basically contains how we utilize finite memory to update our system. Maybe this is not always possible. Maybe we need to have some compromise. But this making good compromise is a technical challenge. Thank you very much.
You mentioned about the unbiased piece and the consistency.
The consistency, yeah.
Is it also important to estimate the barriers and the non-ownership of these barriers?
Right. So if we talk about consistency, so it should be unbiased, and also the variance tends to zero. So in the very strange case, so we have an unbiased solution, but it's not consistent. But as long as we have a reasonable assumption behind data, usually it's no problem. As long as we have a large number of training data, the variance naturally decreases. Then we end up having a consistent solution. Maybe consistency is the kind of minimum guarantee, but we need far better solution in reality. Thank you.
I have one question.
Yeah.
What is the assumption behind the label change? The ground truth label has also some uncertainty, and then they change it to other labels. Is that?
So in the case of, let's say, joint distribution shift,
Yes.
Like this one?
Condition matrix T, right?
okay,
Yeah.
label noise. So in this case, basically, class Y label is flipped to class Y prime. So based on this probability.
Then how about the ground truth labels? They have no uncertainty, or?
No. So there's like P of Y given X. So maybe I should use this slide. So this is the kind of clean label that we have. It's also stochastic. And this is transformed into this way. And this is what we observe from as training data. So both are stochastic. So maybe there's no true like true label, but there's a true clean distribution, and this is contaminated in this way.
For some reason, I don't have an example about changing collecting the labels.
Mm-hmm. So, okay, right. This is also an assumption, right? But once we consider joint distribution shift, then basically any case can be naturally handled. So actually, joint shift is quite generic and useful because sometimes like we observe covariate shift and label noise at the same time. Then the situation is quite complicated. But once we consider joint distribution shift, then actually like this method can handle like a mixture of covariate shift and label noise without really knowing that. As long as we have small number of label test data, we can cope with it. Yeah. Is it here? Or? Yeah. Yeah, so in the case of regression, we assume that noise is independent additive. Right, zero mean noise, independent and additive. Then, so they can cancel each other automatically if you have many training data. Then in the end, you have an average solution, and that is consistent if the noise is zero mean. But in the case of classification, the situation is a bit different. If you consider like binary symmetric noise, then maybe it's fine. But in multi-class case, usually it's not true. So then we need a specific noise reduction mechanism to recover consistency. And the way based on noise transition matrix is a kind of systematic way to handle such noise. Noise. Yeah. So maybe the last page is more. This is more precise. So this is input-dependent noise already. So noise transition is conditioned on X. And in the simple case, we just ignore the X like this. So this was the first case, input-independent noise. Sorry. Yeah. So input independent case, so noise property is essentially the same because it doesn't depend on X. But in the input dependent case, we have X. But this is just one example, but any other case could be possible. But maybe this is a natural example that we have more noise near the boundaries because they are difficult samples. And we have less noise here, because they are easy samples. Thank you.
I have another the UU learning, that reminds me the ICA. Is it an advanced version of ICA or completely different?
I've never thought about that. Right. ICA is also a very interesting unsupervised learning, and it is really related to like feature disentanglement. But they are unsupervised learning problem. They only play with features. But this is a like supervised learning problem. So we really try to train a supervised. Try to train a classifier only from unlabeled data. So I think the formulation is essentially different, but there might be some relation behind. I've never thought about that.
Okay. What I said that because this is also the mixture of two classes.
Right.
The ICA signal is the mixture of two classes.
I see. Like for binary classification problem, so we can extend this UU classification to like UUU classification or U to the power of M classifications if you have multiple unlabeled data sets. But for multi-class problem, so the UU classification is not that straightforward because once we have, so if there's only like one unobserved class, then this is possible to solve. But for three-class problem, we can't really distinguish like three classes only from unlabeled data. Maybe this is somewhat similar to the like permutation problem in ICA. So we can somehow identify components in some way, but we can't really, I can say, align them in the right way because there's no information. But right, if we have some additional information like non-Gaussianity or something, then that information could be used to align unlabeled classes. So, no, I never thought about that direction, but that must be quite promising. Thank you.
Other questions?
Oh, yeah. Page 30. So 30, so I can.
It's my
Yeah.
I'm afraid that I might miss your explanation, but I'm still wondering that how we can achieve, how we can obtain the PTEOX over PTR over X. I mean, my goal is that PTE over X and PTR over X either still unknown. These are kind of underlying density function.
Right. Like we have two sets of data. So training data is coming from PTR, and test data is coming from PTE.
Is it right that we instead use model prediction instead of?
Yeah, and we try to avoid it. So one naive solution is to estimate PTR from training data based on some model, like a Gaussian model or something, and similar for test data, and then take the ratio of two estimators. But usually, such a two-step approach is not so accurate. So that's why we try to avoid it and directly model and estimate the density ratio. And like in this case, we have a model of density ratio R, and we try to directly fit our model to the true density ratio by least squares in this way. So the equation is a bit complicated here, but once we expand this square term and ignore some constant, we have very simple equation like this. Then this part can be estimated only from training data, and this part can be estimated from only test data. Then we can minimize it. This is a consistent solution. Okay.
As I understood, in this equation, PTEOX over PTROX is like ground truth.
Right.
And the point that I wondered was how can calculate this ratio even if we don't know PTOX, PTROX?
Right. So we just assume it exists, right? This is the quantity we can define, right? Then this is still unknown, but we try to fit this one to unknown density ratio. But in the end, density ratio does not appear here. They are cancelled each other. So this is a kind of nice mathematical trick. Because the ratio has a specific form and so we have PTR here. Then like first term, so we have R squared PTR. So we have this term. Then, so 2 times R PT over PTL and PTL, and these PTL are cancelled, and we have this one. Then in the end, everything becomes quite simple.
But later we use data. Using this equation, later we use data.
And target here is to avoid estimating the density directly.
Then it requires two-stage training.
But in this case, it's one step, because we don't have to model densities, but we just directly fit R to the true ratio. It's a bit tricky, but yeah.
Yeah, if you have other questions, we have one more time to discuss. No, nothing. No. Okay, thank you everybody for coming here and asking many good questions, and also let's thank the speakers for
Thank you very much.
very, very good, inspiring talk. Thank you.
Thank you. Questions are so good.
Yeah. Well, I think you gave them many inspirations. There were very small number of people coming here giving this kind of study.
Oh, yeah.
Yeah.